Right, hello, hope you're doing well. We're going to cover oxidation states and specifically how to assign them and how to use them to tell if a reaction is a redox reaction. At the end of this worksheet, I have some information with redox, and one of the parts of it is how to assign oxidation states. So a lot of this stuff you know from charges of ions, and in those cases, the charge of the ion is the exact same thing as the oxidation state. In some cases, there's a slight difference. Oxidation state is a more general idea that can apply to things even in molecular compounds that we wouldn't say are actually ions. And so the rules are laid out here, and they're essentially a hierarchy. So just to give you an example of one that's might be kind of tricky, would be something like maybe this compound. So we know that this is not an element, it's a compound, so we can skip number one. The rule number two is really going to be the one that you probably use most often. You want to make sure the charges add up, or the states add up to the charge on the molecule or ion. This is neutral, so everything has to add up to 0, right? Okay. When you go down, the numbers take precedence over the other ones. So first you would use rule 3 and assign potassium as a +1 oxidation state. So down here, if you want to keep track of that, you would then have 2 +1s, right? So in this case, if you assigned oxygen as -2, that's actually incorrect, because you would have 2 times -2, and that would not add up to 0. So that's why we want to assign potassium first. That's rule 3 before we do oxygen. And if we do potassium first, we realize that the oxygen has to be -1. And only in that way will these oxidation states add up to 0 because it's neutral. So this is the case of this is a peroxide, right? So this is actually potassium peroxide, not potassium oxide, which is a more rare form of oxygen, a much more reactive form of oxygen, but it does exist. Okay, so I wanted to point that out to show you kind of the hierarchical nature that if you get a kind of a tricky one, the lower number rule supersedes the other ones. So there is a kind of a importance to how these are numbered here, but in most cases you're not going to really need to utilize that because you'll just have common things that you pretty much used to. So as you kind of look at something like ammonium, write this here. So we know that the charge is +1. So this means that all these states have to add up to +1, right? So then if we go through our list, we don't see nitrogen. Oh, I see hydrogen, rule 6. That's +1. Okay, so we can assign hydrogen as +1. And then we have 4 of those. That's 4 times +1. If we don't know what this is, we can just call it X, right? So kind of like nitrogen is an unknown, but I know there's 4 hydrogens. That has to add up to 1. Oh, let's solve for X. X has to be -3, right? So pretty much when you answer this, you would say nitrogen is -3, hydrogen is +1. You always want to indicate the state for each atom. In other words, you wouldn't say +4, that's the state on all of the hydrogens. You would just say the state on each one, which is +1. Okay, hope that makes sense. That's pretty important. All right, so just kind of, again, breaking these down, you can go through your list, always remembering what they need to add up to. This is neutral, so it's going to add up to 0, right? And if you go down the list, you're going to have group 1 metals, that being kind of the first priority. So let's assign this is +1. So we're going to have 2 of those. Okay, carbon, there's not really a rule. Oxygen, there is a rule for -2, and that's mostly what it is in most cases. So now we have 2 times X for carbon and 4 times -2 for oxygen. So we can easily figure this out using some algebra. 2X has to be 6. So we have X being 3 plus 3, right? So we'd say sodium +1, we'd say carbon +3, we'd say O -2. All right. And lastly, lead sulfite. Okay, so with this one, if we go down the list, basically the only thing we can assign is oxygen. We don't have a rule for lead. Lead's a metal that can have various charges. Sulfur also, there's not really a rule for. It can have various oxidation states. So you might be kind of stuck here, but what I'll point out is it is a really useful trick with these is if you can recognize the polyatomic ions, right? Which we do have one here, which is called sulfate. Okay, so sulfate has a -2 charge. And I should maybe get rid of this thing. It's kind of confusing now. This being the charge of the sulfite ion. So when we break this down, we can basically do this, right? Because we know O is -2, and this has to add up to a -2 charge, which is the charge of the polyatomic ion, right? So now we have a case where we can actually figure out, oh, X -6 equals -2. X has to be +4. So that, and X is sulfur, right? So we basically figured out sulfur is going to be +4. O is -2, and then we only have one unknown, which that's the only way you can solve something is if you just have broken it down to one unknown. So now we can do X +4 -6. This is all neutral, right? And then X is going to be +2, which you could have also figured out because the lead is paired with sulfite, which is -2. So this is actually lead 2 sulfite. If you broke down the name, that would be another way. It's pretty much like, simultaneous way of figuring out the lead charge. Okay, so that makes sense. Just again, do some kind of practice problems and then you'll get the hang of it. But these are important because they're used in lots of other kinds of questions and concepts. So if we look at like a problem where you want to identify if it's a redox reaction, a redox reaction will have a change in oxidation state. And on the worksheet, I also have some definitions of oxidation reduction. So I'll get to that in a second, but let's just kind of break down how we can figure out first if it's a redox reaction, and that is pretty much to assign oxidation states. Okay. So just kind of going through, oops, start with the first one. Each element in each compound, doing what we did before. I won't spend time on that because that's kind of what we did before. But you're basically going to get these numbers. I'll write this one up here, +4 -2. Okay, and then we have +1 and -1. So if this is again not really clear yet, just maybe pause the video, work on this on your own, take some time to assign them, see if you can get these and then kind of come back. So okay. So we have these oxidation states that are assigned for these elements in all these compounds in this reaction, and we want to see if they change. So just start comparing. Sodium is +1 on each side. Okay, hydrogen's the same. Carbon's +4. Over here it's +4. You know, bromide's the same. Oxygen's the same. So basically, in this reaction, the oxidation states don't change. So this is not a redox reaction. This is actually an acid-base reaction. Acid-base reactions and precipitation are not redox. Everything's staying the same in terms of their states. If we look at part B, we have this is actually a combustion reaction, and we're going to see if that is a type of redox reaction. So again, when we go through assigning, we should get this, again, using the rules and the method before. O2, okay, so here's a good one to kind of talk about for a second. Do we assign -2 because it's oxygen? We do not. The first rule is that elements are 0. So be careful if you're just kind of going based on patterns like, oh, oxygen, always -2. Actually, as an element, it's 0, right? Okay, so CO2, we can do oxygen here is -2, and then carbon would be +4, and then good old water, seen it before, pretty much the same, +1, -2. Okay, so do the oxidation states change? Well, if you look at the first element in the reactant, carbon, -4, in the products, +4, it's changing. When you find something that's changing, this indicates it is a redox reaction. Okay, so now we wanted to also identify what's oxidized and reduced. The oxidizing and reducing agents, the number of electrons transferred. Okay, so what I would recommend is, which I have on my end of the worksheet, is some kind of mnemonic. I like this one with the arrows. So oil rig means oxidation is loss of electrons, reduction is gain of electrons, and then the arrows tell you about the increasing or decreasing state. So oxidation is increasing the oxidation state, reducing is, as it says, reducing the oxidation state. That's often easier to use. So if I use that, like let's look at carbon, right? Carbon is going from -4 to +4. Is that going up or down? That's becoming more positive, it's going up. The kind of weird thing is that we actually say the whole reactant. So CH4 is oxidized, even though it's just the carbon in it, right? We use the whole reactant. We say the whole reactant. And what's reduced? So if we look at oxygen in the reactant, it's 0. In the products, it's -2. So the O2 reagent is reduced, right? It's going down. The oxidation state's going down, right? Being reduced. Okay. So here's the confusing part. The thing that's oxidized is known as the reducing agent. Again, I have this definition on my worksheet. You just have to maybe write it down for now or just try and memorize that. It's all kind of opposite when you say the agent. Thing that's oxidized itself is actually the reducing agent. The O2 is itself reduced. It's called the oxidizing agent. All right, I know that's totally just, a mind trip, and kind of might seem like, why is it, or we're making it this confusing? But there is a reason for this. There's a kind of a riddle that I've heard that says, what gets wetter as it dries? So what gets wetter as it dries? And the answer is a towel. So a towel dries something else, but it gets wet. And to me, that's the best analogy I can kind of come up with of what this means. So a towel is a drying agent. It dries something else, therefore it gets the water. So if you think about oxygen, it is gaining electrons, right? It's reduced. Oxygen's taking electrons. So what it's doing to something else is it's oxidizing something else. It's allowing something else to lose electrons. It's like the towel, right? It's the agent to oxidize something else. Okay, hopefully that makes a little bit of sense. Just kind of think about the towel analogy, and maybe these, when you say agent, that might kind of help, hopefully. All right, and the last part is just to figure out the number of electrons transferred. So if we look at the carbon, it's going from -4 to +4, right? So it's losing how many electrons? Well, it's becoming more positive by 8. So therefore, it's losing 8 negative charges, right? And there's only one carbon. So basically, we've actually just found the number of transferred. Because if something loses 8 electrons, something else has to gain 8 electrons, right? The only thing, kind of caveat, is if I look at oxygen, kind of this oxygen here that's going from 0 to -2 over here, we would say, oh, it's gaining 2 electrons. Hey, that doesn't match. But this is where you'd have to think about the number. So that's each oxygen. How many oxygens are in the reaction? There's actually 4 of them, right? There was only one carbon, so that's why we could just say loses 8 and stop there. But for oxygen, it gains 2 electrons per oxygen. So we actually want to multiply this by 4, and then we get gains 8 electrons. And that matches, right? It has to match. So there's 8 electrons transferred. That's I guess, our ultimate answer. The same number has to be lost and gained, right? Okay, so if you find an element there's only one of in the reaction that's changing, that's the easier way. If you find, the other one, you have to then multiply by how many, like, oh, each oxygen gains 2. There's actually 4 O's in the reaction. That'll give you the total. All right, I know this topic can be kind of confusing. Redox just is a little bit, that's the nature of it. But hopefully by doing some problems and practicing and just kind of learning definitions, it'll make some more sense. In the next video, we'll cover how to balance reactions by the half reaction method. Okay, we'll talk to you then.